Hello, welcome back to Introduction to Computer Networks at NTU. Guys, welcome back. And Katie, right on time. This is week 9, episode 16. So what we have due this week is PA6. So this one should be rather straightforward for you guys. And then we have 4 quizzes due this week. So among these 4, 23 and 25 are straightforward. Okay, it's just to exercise the finite state machines or the mechanisms you learn. 26 is open-ended. Okay, a little bit crazy. You know these open-ended problems. They will sound irrelevant to what we're talking about in computer networks, but they are actually relevant. Okay. So you exercise associations with these open-ended quizzes. And quiz 24, this one is a little bit tricky, okay? But it's necessary to make sure that you understand something, the complexity in TCP's reliable data transfer. Okay, so that's what's coming ahead this week. And guys, sorry, exam 2 is coming up in about 2 weeks, okay? But you know how it likes taking an exam for this course. I guess for some of you, it's straightforward. It's just that there's time pressure. So see if you can find time to exercise more. That usually makes it easier for you. In fact, you guys already do very, very well. Polly is going to have a hard time grading at the end of the semester. Okay, so I'm not sure I should be happy or sad, right? I'm happy in a way that you guys pick things up really fast. I'm sad in a way that I might need to explain to the university what's going on. And it's something that I don't fully understand. And I'm very happy that some of you did send me tips, okay, suggestions. Thank you guys. And hey, Yixin, no worries, be happy. I think Polly is the one should be worried, okay? And after Katie, let's see, Yu Zheng, Qilun, Alan, Vincent, Yuxiang, good job with the exam. I think P12 or P13. Okay, so take Polly's admiration. Okay, Yuxiang, and then Yingxue. Okay, all good. Good afternoon to you all, and let's go on to the topics. Before we start introducing TCP's reliable data transfer, Polly has something, okay, needs to discuss about selective repeat. That is related to the sequence number space. Okay, recall, in pipeline RDT or in any RDT, we use the sequence number to indicate individual packets. Okay, which one is the one we're sending, which one the receiver needs to add. That sequence number space in the packet, okay, if the sequence number space is large, then you ended up having a large field there in the packet. So it's not good to be too large, but it's not good to be too small either. Okay, in selective repeat, the sequence number space needs to be larger than 2 times the window size. So 2n to be exact. And to explain, I'm going to use a scenario, which is a little bit tricky. Okay, so this video, 6.5 minutes, introduces this tricky case, and so that you get an idea why the sequence number space needs to be larger than 2 times the window size. Let's see if you can follow. The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay, but from the reviewer's point of view, they will actually look the same. Right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ACK 0, ACK 1, and ACK 2. So ACK0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next ACK, that's going to advance the send base further to 2. All right. And we generate yet another packet to send. And the next one will be what? Yeah, carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? Right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK0, ACK1, and ACK2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right. So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. Now, this is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the what? The application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent packet 0 here and packet 0 here obviously are 2 different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. Right? So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay, can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So the receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any ACKs back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. Right? So they are actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Isn't it obvious? The sequence number, make sure that the space is larger than 2 window size, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window. All right, so you will never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size. All right, so that's the trick. Okay, and that's the scenario illustrate why 2 times window size is necessary. And now we move on to introduce TCP's reliable data transfer mechanism. In this overview video, which is a little bit long, 6.5 minutes, you will see that TCP's RDT is just like the pipeline RDT, but you will see also that TCP's RDT, in many aspects, also more general than the pipeline RDT. And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are 2 minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. By 0, by 1, by 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet-to-packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there, where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Okay. Now, what we don't know quite yet is this. This window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear. It's also for the congestion and flow control. Okay, so there's going to be a window size for flow control. And the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see, what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right? Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion. But it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet.
Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages in the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACMEX messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number, we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data.
All right, so now let's get into the detail. And first, let's start by talking about TCP's packet format. You will see that in the packet header of TCP, there will be some fields that we also see in UDP's packet header. But there will be some fields being added so that the TCP can implement this reliable data transfer mechanism. Okay, so this video, 5.5 minutes.
TCP segment structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP we do have these fields: source port number, destination port number, as well as the checksum. Okay, so all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. Okay. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, in this field, the length. Do we have lengths in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header lengths, why don't we talk about these special bits, special flags in the TCP packet header? First is the A flag. So this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, conveniently, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to reinitialize certain parameters between the sender and receiver of a TCP. And P bit. P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. So you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call, to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent, critical data transmission. And we said that these are not used, so there are a number of bits not being used. But the fact is, actually, there are two more bits being used. It's called the C bit and the E bit. Now, these two bits are not really for reliable data transfer service, not for connection management purpose. They're actually there for congestion control. But it's not quite the congestion control implemented in TCP, though. It's just that the engineers are expecting later on TCP's congestion control can be extended together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. This is the window size for the flow control. If you recall earlier in the overview, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. The sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, not packets.
All right, so next is to talk about exactly how we count the bytes. So this video, 4.5 minutes, and you will see that as we assign sequence numbers to the data part as well as the egg part, we need to count how many bytes are there in the packet. So let's see if you can follow.
TCP sequence number and egg numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on and so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? Oh, the byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you, TCP implements, just like go back in, cumulative acts. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet, but now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so add number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go back in. So if you recall, go back in's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them.
All right, so you see that instead of counting packets, we count bytes, right? So packet 1, packet 2 is actually relatively where the data is in the original message. Byte count 1, byte count 2 is also where relatively the data is in the original message. It's just that the granularity now differs. And the strength of counting byte is such that we can track where the data is missing in the original message in a finer granularity. Okay? And that allows sending of data packets over TCP connection to be flexible. So if you have a lot of data in the original message, you can use the maximum segment size, for example, for each of the packet. But in case the original message is short, right? You don't need to pad everything until a full packet is full, and then you send the packet, counting data by packets. Okay, you can count like 3 bytes of data sent. So you can send variable packets, variable size packets over a TCP connection. Okay, so finite granularity, more flexibility. But that makes things a little bit complicated, but no worries. Let's try follow through this example. It's to send a byte over a telnet connection and see if you can follow assigning the sequence number and ACK sequence number to the packets that we're sending.
Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Okay. Now because it's a very straightforward character C, not like escape or control C, therefore what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number we'll be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number. Yeah, the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? The last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, yeah, we say ACK 43. And this is also host B telling host A what is the next data byte expected. And therefore, we see the next packet coming back from host A, sequence number 43. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So ACK packet needs to be what? Last byte received by host A, which is 79 because there's only 1 byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction.
All right, so let's exercise. Okay, I think you guys are fine. So this is quiz 23. Let's exercise by counting. On the left, you see a more straightforward example, which is one directional, unlike in TCP that is bidirectional. And let's check out the simple case first. Host A, okay, sending data to host B. So host A sending data to host B. And this first exchange, starting from sequence number 100, and there's 8 bytes of data. All right. So the ACK sequence number will be what? The last byte would then be 108, actually 107, isn't it? Because first byte is 100, the last byte 107, and plus 1. Right, so that's how you assign the ACK sequence number. Okay, and there's no data going this way, but there's another packet coming after receiving ACK 108, right? And this next packet is 12 bytes. So the end should be 119. And therefore plus 1, yeah, the ACK 120. Now let's try this more general case, which is more like TCP, sending data bidirectional. So we have A and B, and they are sending data in between each other. Therefore, you see, from A to B, we have data 20 bytes. And B, of course, needs to send an ACK for this data packet. But B also has data to send in 100 byte. Okay, so can you figure out how to assign the sequence number and how to assign the ACK number here, which is A and B? And upon receiving this packet, A sends another packet. There. Can you assign the sequence number and the ACK number as well? Similarly, for the further packet going this way, E and F. That is quiz 23. Let's go to the Discord space. Oh, wow. Okay. Yeah, it looks like you guys are fine. Guys, you have 2 minutes. Okay, let's start counting time. So Polly is also working on this just to make sure that you guys are getting things right. So C will be B. And D will be A plus 100. And A is 100, so 200. E will be D. B, C, D. D is 200. And F should be C plus 20. C 1, 2, C 160. Let's see. 140, 140, 200, 200, 160. Great. All right. Vincent, 200, 200, 160. There you go. 正年. Okay. All right, time's up. As I have projected. Yeah, I think you guys pick it up. So we just count the data by bytes instead of packets. And so that you see, oh, data can be 20 bytes long or 100 bytes long. And we don't need to pad packets or maintain a really, really long sequence number. And send, when we are recovering, we send small packets and jump to a farther away sequence number. Or, yeah, you know, you get the idea. Okay. So we count the data tightly this time, okay, in TCP. Very good. Do I have 4? No, I don't have 4. But guys, as long as you are answering this question within a certain amount of time, I'll just, you know, take that you guys pick it up. It's just that there's a slight different variation in completing. Oh, look at this. Yende, great job. So Team 10 actually tells exactly how they derive the numbers. Wonderful. Great, thank you. You see, it sounds odd, right? But once you know the rules, it's straightforward. Okay, so a lot of times these mechanisms we'll be introducing in the class are like this. Once you're familiar, it's really straightforward. All right? Now let's come back, guys. Yeah, we need to introduce more details about TCP. So the next thing is this. In RDT pipeline or RDT stop and wait, either way, in order to address this particular scenario of packet loss is this particular scenario, having packet loss, we set a timer. When the timer times out and we don't receive an acknowledgement back, we retransmit, isn't it? This is the Lord of the Ring quiz. So previously we just say that, hey, after timer times out, expires, we retransmit. We never talk about exactly how the timeout interval is. Hey, TCP being a real mechanism that we implement, of course, right? The engineer needs to set a proper timeout interval. Okay, so this video coming up next explains or discuss it's actually not okay to set the timer to be too long, and you can imagine why, because longer delay, right? Therefore, some of you guys says that, hey, if I receive a negative acknowledgement or acknowledgement indicating that, hey, there's a bit error in the packet, that's quickly retransmit instead of waiting for timeout, because usually that's a longer time. So set the timeout interval long, of course, that's really bad. But if you set the timeout interval really short, that is also not good. Okay, so here's the discussion, and you will see why setting it too short is not good.
Now, with the fundamentals of TCP packet format, TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before Polly shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If an ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical. And that interval determines how long the retransmission is going to go. And that influences the performance of a reliable data transfer. We know already in some earlier example, if that timer is set too short, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard Polly saying this already. The interval should at least cover what? The time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard Polly saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round trip time repeatedly in between the pair of sender and receiver. And this is exactly how it's done. Okay. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a sample RTT. Now, there will be a lot of these sample RTT for each data and ACK pair, but we will ignore the data ACK pairs due to retransmission. So some of these data might get lost, and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these sample RTTs, and they could vary quite a bit. So you see that it's actually not good to use the sample RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent sample RTTs.
All right, so that's the idea to set the timeout interval. You get an estimate of average round trip time and you track it over time. And average round trip time is still average, so there's a high percentage also that there'll be half of the round trip delay being longer than the average. Therefore, you have this unnecessary retransmission. So you want to set it to average plus a margin. Okay, so the full mechanism is in the next video. It's about 7 minutes, so today we'll run over about 2 minutes. Okay, so bear with the video.
So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smoothed RTT next is going to be the smoothed RTT now, and take a weighted sum of that to the current sample of RTT. Okay, so current smoothed RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average, and we're using a spatial factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current, okay, smoothed RTT. Now this whole thing is going to be used as what? The first term of the next estimation. So you see, okay, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay, 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Oh, and by the way, alpha is only 0.125. That is because, we don't want to wait too much on the instantaneous RTT, because otherwise it will be what? Also fluctuating, okay, not exactly smooth. And here shows, the instantaneous RTT and the estimated RTT, the smoothed estimation, how they look like relatively. And this is actually actual measurement between UMass and Eulercom again. So the blue one that fluctuates more, like these. These are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smoothed, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, relatively smooth. And you see also, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, the smoothed average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. So the estimated RTT there is certainly not covering most of the round trip time observations. So there's more. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. And the timeout interval should be the average plus a safety margin there, such that all these simple RTT fluctuates in the middle will be covered. Or, the more simple RTT being covered by the safety margin, the better. Challenge next is to set the safety margin. And the thinking behind setting the safety margin is this. If the sample RTT fluctuates a lot, we use a larger safety margin, right? Small fluctuation, smaller margin. Therefore, the key is to estimate the variation of the sample RTT. So the challenge boils down to estimate the variation of sample RTT. And that can be done this way. So simple RTT is the instantaneous RTT. And estimated RTT, there is the variable storing the average RTT. So the deviation is essentially what? Yeah, the sample RTT subtracting the average RTT. Right? Now, of course, we will not be using this, by itself to set the safety margin, because this is also what? The instantaneous deviation. Right? So let's estimate the smoothed deviation of round trip time, okay, by the EV-RTT, and borrowing again the technique, the exponential weighted moving average, to get the smoothed def-RTT. So the next def-RTT will be the current def-RTT and the weighted sum of that to the instantaneous deviation of RTT. All right, so the only thing left is just the beta factor, and it's also set to a small value so that we weigh less on the instantaneous deviation. As to why it's 0.25, not 0.2, not 0.125. Yeah, these alpha beta values are usually given because people have been using these values and they seem to work out fine, and engineers later on will just borrow using the same setting. And now finally, the timeout interval. It is the estimated on-trip time plus the safety margin, which is determined by the deviation of round-trip time. Now, as to why 4 times the deviation of round-trip time, the original designers of TCP, they don't usually talk about this. I mean, the 4 could be a result of repeated experiments, but Poly guessed also it could be because of this. They have assumed the sample RTT distribution being normal. If you recall back in Statistics 101, right, normal distribution is for a sample such that if you plot the histogram of that sample, you see a bell shape. The average is usually in the middle where there are lots of samples, and the 2 ends, few samples. In normal distribution, starting from the average, if you add 2 standard deviation, subtract 2 standard deviation, it should cover what? 95% of the value range of all these samples. So by adding 4 standard deviation here, timeout interval here is covering more than 99.99 something percent of these sample RTTs. That is also saying, setting the timeout interval this way, there's going to be very few premature timeout in TCP.
Yeah, so the mechanism setting out the timeout interval makes sense, isn't it? All right, and with that said, this is all for today. We'll continue to introduce the details of TCP's RDT tomorrow. Okay, and with that said, I say goodbye. See you tomorrow. Bye. All right. Okay, tomorrow.